That's enough storytelling about structures. Let's get back to the chapter. Trusses. The assumptions for trusses are that the loads are only at the joints and all the members are two force members only. Axial forces only, which means no moments. What that also means is if you have a member like this, the force has to be directed along the length of the member between the two joints. There are two ways to solve truss problems. The first one is called method of joints. We're going to do that. It's very methodical. I will go over the procedure that's actually in the book. We'll do some problems. And then when we're done, I'm going to show you a shortcut method that I use that accelerates it very quickly. This shortcut method you're free to use whenever I'm your instructor, either in this class or future structures classes. There are not many other professors here, or maybe not many anywhere. This is kind of an old technique that use my shortcut method. It's the only way I do trusses, but I'm just warning you, if you take a class from another professor, especially if you go into civil or architectural engineering, if I'm not your professor, you cannot use the shortcut method I'm about to show you. So you have to know the official method. So I'll go over the official method first, then I'll show you the shortcut method. Here is the official procedure for finding all the forces in a truss using the method of joints. Step 1, draw the free body diagram of the structure. Step 2, solve for the reactions. Let me stop here. Steps 3 through 5 involve a lot of tedious work, and if you get step 2 wrong, everything you do in 3 to 5 will be wrong. Well, if you draw the FBD incorrectly, you're not going to get the reactions right. So steps 1 and 2, which we've practiced ad nauseum in chapter 5, are super important for this. Make sure you solve for the reactions correctly. This next step is optional, but I highly recommend it. Look for what I'm going to call zero force members. I'll have a separate little lecture or YouTube video on zero force members. The next thing you do is you look at all the joints in your truss and find a joint that has only two unknowns, because it's going to be particle equilibrium in 2D. These are all concurrent forces. So you'll have two equations, some fx and some fy equals 0. Thus, you can only solve for two unknowns. After you find a joint with only two unknowns, draw an FBD of the joint, and then solve for the two unknowns at that joint. The opposite of these answer goes on to the neighbors. What I mean by this, let's say this was your joint, and you were given that by the reaction statics, and you had these two unknowns. You could solve for that, and then this, let's say, I don't know, let's say that came out to be 60, and then this joint up here that connected down to there might have looked like that with three unknowns, but since you just solved this one for 60, you can put that up here, equal and opposite. Just remember, let's say this one is pulling away, then on this one up here it's pulling away. Now that you know this 60, there will be two unknowns here, and you can solve for that. And you repeat step 4 over and over until you've walked your way across all the joints in the truss and you've solved for all the forces. This procedure reminds me of the song Dem Bones. It's toe bone connected to the foot bone connected to the heel bone, and etc. So you're going to have a big old truss like this, and you're going to do the statics, and you're probably going to get this force, and you're going to get that force, and this force. Well, you solve this one, and then that means now at this joint you know that one, and so then you can solve this one, which means now at this joint you know this one and this one from the previous two, and you can solve that one, and you just work your way all the way across the truss one after another. You do the one connected to the previous one you just solved. When you do this, it's important to keep track of the signs. And what I'm going to recommend, let's say you find that that's 50. And here you just draw, if it's unknown, draw it pulling away or in tension. These forces are pulling away from the joint and they're in tension. And after you solve for it, let's say this comes out negative and that comes out positive, that means the real answers were like this. Okay. Now, this is very, very important. When a force pushes into a joint, it's in compression. And when a force pulls out from a joint, it's in tension. In fact, this is so important. When you get your answers, let's say it's 60, I want you to write C, or I want you to write T if it's tension or compression. Here's a hint I find very helpful. I've done this thousands of times, and I think this will help you out. I find it easier to keep track of X and Y components and use geometry rather than keeping track of cosines and sines. You might have to keep track of sines and cosines sometimes, but this is a useful technique. Let me show you an example. Let's say you have a truss that looks like this, and here's a joint, and you have a reaction of 40 kips coming up, and this is a 4-3 slope, which makes theta 53 degrees. Let's say that's F1 and F2. So you decide to do sum Fy equals 0 first, and you get F1 sine theta, so F1 sine theta plus 40 equals 0, and you solve for F1, and let me plug in 53 degrees for theta and see what we get. 40 divided by sine of 53 degrees is 50.08 kips, and now we're ready to do some Fx equals 0, and that actually turned out to be negative 50.08, which means it's going that way in compression. Okay, sum Fx is 0, so we have minus 50.08 cosine theta plus F2 equals 0, or we get F2 equals 53 cosine 30.14 kips, and that was positive, so that's that way in tension. Okay, let me show you what I mean by keeping track of X and Y components. So let's redraw that. There's F1, F2, and that 40. And again, this is at 4, 3. And what we're going to do is sum Fy equals 0. And we're going to say 40 plus F1 Y component equals 0, which means F1 Y component is minus 40, or compression. Okay, then we do sum Fx equals 0, and now we have minus F1x because it's in compression and to the left, and the x component, plus F2 equals 0. And now we see that if the y component is 40, the x component of F1 is 30. So minus 30 plus F2 equals 0, and F2 equals 30 kips. And we need to get the total F1, and so F1 equals square root. The x component was 30, the y component was 40, and that equals 50 in compression. This is really better learned by example than by explaining how to do it. And so what I'm going to do is I'm going to do a traditional example using sines and cosines, and this is the official way you need to do it. Then I'm going to redo it just with x and y components like I did there, and We're going to keep the X and Y components separate. And then finally, I'm going to show you this advanced shortcut that I use, which again, you can only use in my classes.